Welcome back to another lecture, guys. As I mentioned, last week we were having some technical issues, which I got some new hardware. And while issues persist, it's a lot better. In fact, this is my second time trying to record this because I ran into some issues recording this lecture. But we're going to continue. We're going to jump right in. Allow me to share my screen. So here we are in OneNote, and as you can see here, we're actually going into a new chapter. So last time we finished talking about optimization. That was the last topic we wanted to do in chapter 4. We are going to move on to chapter 5, and I already spoke a lot about this and made notes and scraps and stuff. I just want to jump right back into it, actually. So, yeah, it's not fun. Okay. So, take 2. And one thing I'm going to do here is I'm also going to turn off the video because I think it's a little bit less glitchy when I have the video off. You don't need to really see me to do this stuff anyway. So you will now just listen to my soothing voice and let the math relax you. Hopefully not too relaxing to go to sleep. So we are going to attack the area problem today. So when we started the class, this was way back in, I don't know, lecture 1, lecture 2, something like that. I remember way back in the beginning of the semester where we spoke about what is calculus? And we started a discussion about what do you think it is? And we saw that it was the study of limits and derivatives and integrals. And integrals is the last thing, as you can see, we're going to cover here. And that is all true. And we also went into the direction of talking about, well, why do we study these things? What was the whole point in developing these mathematical objects, these mathematical notions? And the idea was there were 2 main problems that calculus was meant to solve. These were the rate problem and the area problem. And it turns out in solving these problems, we got so much more out of it. But these were the 2 big goals of calculus, let's say. So the rate problem is kind of what we've been dealing with this whole time. And it was the problem that basically said, okay, how fast is this thing changing, right? So the rate problem was a question of figuring out the rates of change of some quantity that you're interested in and that you're measuring. And we saw that the derivative was the solution to the rate problem. It provided a way to talk about the rate of change of something that you can track with a function. Provided the function behaved nicely, you can take limits and all that good stuff, and the derivative limit existed. You could use this idea, this notion, to actually talk about the rate of change of the function that you're looking at, and therefore talk about the rate of change of whatever it is tracking. The next problem, the second major fundamental problem that calculus was meant to solve, is the area problem. Now, this is the idea or the notion of figuring out how much space something would take up. And how much space something would take up is really in terms of, area, or, in higher dimensions, volume, hypervolume of that, or anything of that sort. But really for us, it's going to mean area. So when you start to talk about figuring out volumes and really being sophisticated with measuring that, you're really getting into the realm of Calc 3. We're in Calc 1, so we're going to keep it very basic. We're talking about how much space something is taking up in terms of area. So the idea is we want a very good way to measure how much space something takes up, and there can be a very good cause for this. Now, if the shape that we're talking about is some nice shape, like a rectangle or a circle or a triangle or a trapezoid, or any of these nice shapes that you've seen in high school geometry, then the problem is not really a big problem. We have nice formulas to find out the area that these guys take up. However, what if I asked you something stranger? What if I asked you, well, what is the area of that, right? Well, we don't have a nice formula for a random shape like this, right? So that is the idea though, but we might want to know how much space something like this takes up, something random. And we've seen examples like this in class before, and I've mentioned it again, this is way, way back. So one example is, let's say on a map, this is what a plot of land looks like, and you're the owner of the land, and you're being charged property taxes based on how much land you own. Well, the question is, well, how do you know how much land I own, right? Measuring the area, or how much land, how many acres of land you actually have, if it's an irregularly shaped plot of land, that is a big deal. It's important, has a lot of consequences for you, right? So that's one situation in which you might want to figure out how much space something takes up, something random, some random shape. It's very irregularly shaped that we don't have a nice formula for. How do you go about answering the question of space? Okay, and now it turns out that the solution to this problem, the solution to the rate problem, is one that we've known how to solve for a while. There is evidence that Archimedes, which, as you can see, lived in 287 to 212 BC, there are cases that we know for a fact that he knew how to solve the area problem. So the solution is actually not anything too complicated. What is the solution? How do you actually go about finding the area of an irregular shape? Well, the idea is this. Slice it up into smaller shapes for which you do know how to find the area of the smaller shapes. So take this random shape here, which I don't know how to find the area. I slice it up into a bunch of rectangles, right? Now, for each of these rectangles, I know how to find the area of those guys, right? Because it's just length times width. So the idea is to cut up a larger shape into smaller ones. And the area of the large shape, what we can do is we can define it to be the sum of the areas of the smaller shapes. So I have this irregular shape. What I can do is actually just cut it up into smaller shapes that I know how to find the area of, and then just find the area of each of these individually, add them all up, and that's it. Now, of course, there are some issues here. You'll notice that if the shape is very irregular, then your nice shapes aren't going to fit very nicely. There are going to be little crevices and things here and there. And there are going to be spaces where a full rectangle doesn't quite fit. Now, there are ways around this. You could start dissecting even smaller rectangles to kind of fill in the gaps. But the idea is the more rectangles you use, the better the approximation of the area is going to be. And we've spoken about how useful approximations are. So I don't want to get into the fact that is approximating with rectangles the best thing that we could do. There are going to be ways that we can actually get around this, which we'll talk about later. So that is actually the solution to the area problems. Spoiler alert, I guess. That wasn't very long to figure out how to solve this problem. However, here's the issue though. We want to be able to do this, pretty efficiently at any given time. Like if every time I need to find the area of some random shape, I got to get somebody to slice it up and have him sit there and count up how many shapes he sliced it up into and the area of each shape and add it all up. It's going to take forever, especially if I want to get a really precise measurement, right? So this idea, while it is crude and simplistic and effective, it's just way too inefficient. We need a better way to actually get to the area problem, right? So how do we not have to waste the manpower to have a bunch of people sitting around counting up, adding up all these areas? How can we make it more streamlined? And the idea is, well, let's use the math. We've developed all this theory about functions, and we have the XY plane, which was so graciously given to us by, I don't want that, by Descartes. So what we can do is use our math to help us. Take this shape and put him on the XY plane. Then we are now have him in an environment where we can actually use our math to help us figure out the area. And how would one go about actually doing this? Like how would we make this streamline the process? So here's the idea. Okay, so we're gonna take our shape. Here's the shape. Okay, now, obviously, the next thing is we are going to dissect the shape. Oh, I didn't want to do that. Undo. Okay, so we're gonna slice it up. Boom, 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 boom. You have to make the sound effects while you're doing it, or it doesn't work as well. Now, it turns out, because we're going to try to get some math theory to come to bear on the problem here, this is actually a little bit more complicated than we'd want. Now, obviously, to get the math to work out, I'm going to need a way to keep track of how I'm slicing this thing. So with this, I have to keep track of both horizontal and vertical lines. Doable, but a little more work than I would want to have to do. So here's what we're going to do. Instead of cutting it both in horizontal and vertical directions, I'm going to stick to one direction and slicing them. So I'll only have to keep track of the vertical lines, right? Which I can have one variable keeping track of these vertical lines, right? Like, so it'll go along the x-axis. I can say, oh, for this x values, these are the x values at which I'm drawing the vertical lines. So that's going to be nicer. So now with that, what I'm going to do is let's throw this guy on the XY plane, as we've started to mention before. So I'm going to put this on the XY plane. Right? Now, it turns out that there are immediately some issues with this. Okay, now what is an issue that arises? What is the issue that arises here? Well, when I put this guy here, if I were to draw a vertical line cutting through this guy, it turns out that I would actually cut it in two places. This means it's not a function. It fails the vertical line test. Right? Now, in general, nothing is wrong with not being a function. However, we spend a lot of time on functions. I'd like to be able to use a function to help me. Not having functions is a little bit more complicated. So for example, if I wanted to start to describe the curve that is in the XY plane as an equation, y equals something, well, if it's not a function, I can't really write it as y equals something. And that in and of itself has its own issues. So how we're going to deal with that? Well, basically the idea is going to be the following. We can deal with that by doing the following idea. What we're going to do is, let's just work on one part of the function at a time. So here is the top part of the function, and obviously there's the bottom part, but we don't care about the bottom part. So for the moment, what I'm going to do is I'm going to focus on the top part of the function. Well, the top part of the shape. Why? Because now that passes the vertical line test, right? So a vertical line will only touch this once. Now, yay, this is a function. Now that actually gives me some options. Another thing though, it's actually right in my X and Y here. So now, okay, so far, so good. Let's move down here. Now, what issues can anyone possibly bring up with this nice looking thing? Let's get rid of these. Okay. Oop. Actually want to get rid of the little red dot, but never mind. It's not worth hassle. Let's just fill it in. Okay. One thing is, the strips are still weirdly shaped. Okay, so the idea is to get nice shapes that what we can figure out exactly what the area is without too much trouble. So as it stands, like this shape right here, like what is that shape? Look how the top of it is. It has a very irregular shape along the top of this thing. So what we would do here is try to make it a little nicer. Slice straightly across, horizontal lines across. So now what you'll notice is now our shapes are rectangles. And now we're in a situation where we can actually use these rectangles to approximate the area of the shape that we wanted in the first place. So we are now in a situation where we can actually essentially just think of this object as the stack of rectangles. Now, of course, there's a shape out here which we care about, but essentially what we can do now is approximate the area under this shape using by adding up the sum of these rectangles. And yes, we are going to miss some pieces of area, but if your approximation isn't good enough, what you can do is you can just use even more rectangles, right? Fill in the spaces a little bit more. And that, so now, now we have a good thing going here. Okay, so we started out wanting to find this area of this random shape. So we slice it up into some nice little shapes that we know how to find the area of. A little bit too complicated from a mathematical perspective because I'm going to want to keep track of how I'm doing the slices. So simplify it a little bit, throw it on the XY plane. It's not a function. Let's worry about finding half the area or just the top portion of the area at once. Once I figure out a nice mathematical way to find the top portion, of course, I can just literally just flip that idea upside down to find the area of the bottom portion as well. However, we don't have really these things that we want very nice smaller shapes. They're not very nice. So what I do is I slice off the tops somehow. I come up with a way of choosing how high, where do I want the top of these vertical strips to be? And I just slice across horizontal along those tops. Now I just have a bunch of these rectangles. What I can do is add up the area of these rectangles, and that was going to give me some sort of measurement, some sort of approximation for the area that is under this curve, which ultimately is half the area of the shape that I would want. So the idea is, now if I know how to do this, I would ultimately be able to figure out this, right? So that's the really big deal. And now you might say, well, there are all these missing pieces. And the idea is, yes, we are going to miss some bits of area, but here's the thing though. So I can have this guy, I can have some shape under which I need to find the area. So there's some shape right here. And let's just actually follow this. Paste. Paste. So let's say we want to find the area under this thing on some interval AB, which we'll make this a little bit more precise. And I can use, boom, two big rectangles under this thing. And the area of this guy is what I'm going to use to judge as the area under this, this curve right here, right? And so you might say, well, look at all this area that you miss here. And I'm like, okay, what I would do instead is let's use 4 rectangles to guess the area. And then you might say, yeah, I mean, you're missing a little bit less than you were last time, but you're still missing some. And then I can say, okay, now let's use even more. Now, as you can see, the more rectangles I use, the more of the missing area that I'm filling in. And so now you might say, well, yeah, but I really want to get to the exact area though. Like, what is really the area under this thing so that I can find the area of this object that I really, really care about? And the idea is, theoretically, what we can do is, well, okay, if you really, really want the exact area, essentially what we can do, the idea is going to be, well, let's use an infinite number of rectangles. Let's put in so many rectangles that no matter what spaces you're concerned about, eventually all these spaces will be filled in, right? So it's an infinite number of rectangles. Right? So it's filling in all these little spaces that you're caring about. And if there's a space that's still too large that you care about, let's throw in some more rectangles. Let's do some more. There's always more, right? The more rectangles we use, the better the approximation is going to get, because the more space we'll be filling in, right? And so if you want to fill in all the space, theoretically what you would have to do is use an infinite number of rectangles. Now, what does it actually mean to use an infinite number of rectangles? Of course, in reality, you might say you can't actually do that, but let's hold on. Before we worry about finding the exact area using an infinite number of rectangles, let's go back to this kind of situation here. And how would we actually go about in finding an approximation with a finite number of rectangles? 4, 5, 10, 1,000, right? Some finite number. How would we get to an area in that case, right? So that leads us into actually what we want to do here. So this leads us into section 5.1, where the topic is called the definite integral. And I'll explain what that is later. But this is basically the idea. We want to attack the area problem. That is, how do we find how much space some irregularly shaped object takes up? The idea is to slice it up into strips of rectangles that once we can throw it on the XY plane, we can find the area of these rectangles. And the more rectangles we use, the closer we will get to the answer for what the area is. Now, let's get the mathematical machinery to work here. How would we actually do this? Well, do I want to make this larger? Yeah, let's make that a little bit larger. Now, there are many paradigms for how we can actually get this to work. But there are three ones that we really care about in this class. This is the right-hand rule, the left-hand rule, and the midpoint rule, okay? So those are the three main methods that we are going to concern ourselves with. How do you actually go about getting this done and actually getting some mathematical calculations that make sense that we can use? So the idea is, okay, so I am concerned with finding the area under this curve on the interval AB, okay? So here's the idea. We are going to slice this interval up into several smaller intervals, which we call sub-intervals, right? And so the idea now is we are going to say use n of them. Did I mention using n of them? Right, into n subintervals, right? N is going to be some number that I'm going to actually tell you what that is. Okay, so let's try to guess what the answer is using 4 rectangles or 5 rectangles or 10 rectangles, right? Now, of course, in an actual test, I'm only going to ask you like 3 or 4, but I want to give you the idea that's going to happen here. So we're going to slice it up into n rectangles. Now, one way you can choose into how to construct these rectangles is called the left-hand rule, okay? Now, the left-hand and right-hand rule that I'm referring to here, there are left-hand and right-hand rules in physics and in other subject areas. Well, this one is different from all of those. What do I mean by the left-hand rule for creating rectangles? On each of these sub-intervals, quote unquote, I want to create a rectangle. One strategy is to use a left-hand rule, meaning on the subinterval, the left side would dictate the height of the rectangle. The left side will go up, and wherever it hits the function, that determines the height. The left side goes up, wherever it hits the function, that determines the height. The left side goes up, wherever it hits the function, that determines the height. The left side goes up, wherever it hits the function, that determines the height. The left side goes up, wherever it hits the function, that determines the height. Okay? Now, I actually, now that I'm thinking about this, there's another comparison that I want to make, which is going to be harder to see with this example. So let's actually scratch that. I'll use a different shape. We'll go over everything I just did. Let's make the shape a little bit simpler so you can see something, okay? So let's say it's going up like that. So it's just a curve like that, okay? So again, the math we're going to do, how are we going to set this up? We care about finding it on the interval AB. What we're going to do is we're going to slice up that interval into quote unquote subintervals. For the left-hand rule, the left side goes up, touches the function, that creates the height. Left side goes up, touches the function, that creates the height. Left side goes up, touches the function, that creates the height. Left side goes up, touches the function, that creates the height. Okay, so I have these rectangles here. The area of that is going to approximate the area under this function on the interval AB. Okay, so this is called the left-hand rule. There's another way to actually go about this called the right-hand rule. Now, the idea is very, very similar. The difference is this time we're going to let the right side determine the height. So the right side goes up, touches the function, that will determine the height of that rectangle. the right side goes up, touches the function, that determines the height of that rectangle. The right side goes up, touches the function, that determines the height of that rectangle. The right side goes up, touches the function, that determines the height of that rectangle. And now I have these rectangles over here. And I'm going to use these areas to approximate the area under the curve. Okay, so hopefully that's clear. Now, one thing you might want to do is to make our calculations easier, we are going to make all of these the same width. Which we are going to call delta x. Now, if I'm using n rectangles, or I want n subintervals, quote unquote, how do I know what is the length of each, right? How do you go about knowing what is the length of each? Well, that is to say, can you say, find a formula for the delta x? Maybe take a few seconds and think about it, maybe pause and think about that for a second. Well, one way we can calculate the delta x based on these symbols here, well, if the interval goes from a to b, and I want to use n of these things, where n is just some number to be determined, it's actually going to be b minus a divided by n. And why is that? B minus a is just the length of this interval, right? So let's say this was a 1, and this was a 4. The length of this interval is what? Well, it's 4 minus 1. It'll be length 3. And then I'm going to chop that up into n equal parts. So that is what we have here. So this is actually a very useful formula. It's something that we're definitely going to want to know, right? So I really want to develop a formulaic way of looking at this. Hopefully you got the idea of what we're doing. And now we're really trying to get this down into some mathematical formulas, some nice machinery that we can actually use. There's another way that we want to actually look at of how to actually create these rectangles. And this other one is called the midpoint rule. And here's the idea behind the midpoint rule. So here we have our A and our B. We are going to slice it up into subintervals as we always did, but there's a difference here. Instead of using the left or the right side to actually create the height, what we want to do is to actually find the point smack dab in the middle, and that guy is going to create the height. So this guy's smack dab in the middle of that. In other words, the midpoint between that subinterval, that is what we want to use to create the height of our rectangle. So that point just keeps going up until it hits the curve. And so then it slices straight across. So I use now the midpoint of the subintervals to create it. And so here is the why I wanted to use this kind of function to talk about this. I wanted to show you some of the differences that could happen. Now, because this function is increasing, you'll notice that in this case, now I do want to emphasize that I'm talking about in this case, this guy gives an underestimate of the area, right? Why? Because of course, if I add up all the areas of these rectangles, it's actually going to be less than the area that I actually want, right? Because it's missing some parts. In this case, this guy is an overestimate, right? Because if I add up all the areas of all these rectangles, I'm actually larger than the function here. It covers the area under the function plus a little more. So this here is an overestimate. Now this attempts to minimize the attempts it attempts to minimize error because it gives overestimates sometimes and underestimates other times. So you'll notice for each rectangle, like the left side would be an overestimate, but then it cuts underneath, so it gets an underestimate. So it kind of tries to balance itself out. And again, this is in this case. The shape of your function is going to determine whether you're getting overestimates or underestimates or what have you. So why would you need several methods for figuring out how to find an area? Well, it just depends on, you might want to change your strategy depending on how your function is. If something is strictly going up or strictly going down, the midpoint formula would probably be the best one to pick because it's going to be the one that kind of minimizes the error with the least amount of rectangles. Whereas if your function was kind of bouncing up and down, you might want to pick something else. So it would really depend on what you want. So if you had something like where it's going up on one side and down on the other side, you might say use left hand on one side and right hand on the other side, or a combination of these or whatever. So there are benefits and setbacks to using different ways, especially when you're approximating the area with a finite number of rectangles. In the case that I spoke about earlier, we're using an infinite number of rectangles, then it really doesn't matter which one of these methods I would pick. They would all ultimately give you the same answer. But I do want you to see that there are some differences between these methods. Now, we are going to do examples of each of these, but I do want you to know conceptually that there are going to be issues. Now, another thing that we would do is we would actually start to label what these subintervals are. So for example, oftentimes we would call the A, say x sub 0, it's some x value. The B is going to be x sub n. Now, of course, this is x1, x2, x3, and ... so on, right? Now, of course, the part that hits the function, well, that's going to be f evaluated at x naught, right? That's what that line's going to be. And then the height here, so this is the height. This is going to be f evaluated at x1. The height here is going to be f evaluated at x2, and so on, right? So notice that with setting this structure up on the xy plane like that, if I choose x values to which create the subintervals, I can figure out the heights of the function, the heights of the rectangles, by just plugging in values into the function. Okay, now of course, the idea now becomes let's actually, I probably need to move. Let's move. Move this all down a little bit. So what would happen here is notice that the area would be something like the following. The height of the first rectangle is given by f of x0. And the width of the first rectangle is delta x. So this here is the area of the first rectangle. Plus, I can take the height of the second rectangle times delta x plus, and I can keep going. Now, of course, the xn is never going to give me the value here. The last height that I care about will be the guy that happens just before the xn. So that will go up to xn minus 1 times delta x. Or in other words, this would look like I can factor out a delta x if I wanted to. And I could just actually do that. Add up all these y values, the outputs, which gives us the height of our rectangles, and all the widths. And this was actually would give us a formula for the sum of all the rectangles. Now, there is another way to write this guy. This is using what we call sigma notation. Now, you won't have to worry about this too much, but it's basically just saying it's a symbol that means to add up a bunch of things that have a certain structure. So for example, this is adding up a bunch of things that look like f of x sub I, right? This is x sub 0, f of x sub 1, f of x sub 2, etc., right? Where my I starts at 0 and it goes all the way up to n minus 1. And I'm adding up a bunch of things that have this form. So this here would be the left-hand approximation. Okay. So once we cut it up into subintervals, we have x values tracking those guys, and we will know how to find the corresponding heights of these rectangles by plugging it into the formula of the function. And this expression here actually tells us how to add up all the areas of the rectangles. And this is a shorthand for this entire list right here. Now, with that said, we do come across some formulas that we can talk about in general. So L sub n here represents the left-hand approximation with n rectangles. Here, R sub n is the right-hand approximation, M sub n is the midpoint. Now, this is the formulas that we get from using these different variations. So the left one, it'll start with x0 and then end with xn minus 1, the guy just before the last one. Whereas the right hand, he starts here, that gives you the height. So he starts at x1 and goes all the way up to the last one, xn. And you're multiplying all of these by delta x, that will give you the rectangles. The midpoint, we call these guys, let me actually label those so you see what I'm talking about. This guy here is called x1 star. And then this is called x2 star. This is called x3 star, and so on. Right? So that's what the star here represents. Now, of course, the star, you can figure those out by just averaging the values on either side here. Okay? So if I wanted to find the x1 star, I just take this number, add it to that number, and divide by 2. It'll give me the number right in the middle. Okay? So here are the formulas that would describe these processes. So we go from this idea to something actually very mathematically concrete. It's a nice mathematical form, okay? And note here that the f of xi, these guys just represent the heights of our rectangles. The y value is measuring the height. And while the delta x is measuring the width of your rectangles. Therefore, you're just adding up the areas of rectangles. That's what these forms are saying. It's just different ways of adding up areas of rectangles, essentially. Now, you guys don't really need to know these formulas. I mean, it's very important, and theoretically, to prove a lot of things, you'd want to know this. But in this class, it's an applied calculus class. We're not really going to prove anything here. So this is really what it boils down to. But I'm going to show you guys a way to actually have a shorthand for this. That being said, let's just stick with the theory for a little bit longer and talk about the case where we want to find the exact area. Now, the exact area, This is when we use, as I mentioned, an infinite number of rectangles. How do we get to do that, theoretically speaking? Well, we could never actually get to use an infinite number of rectangles. The more rectangles I throw in, it's never going to be infinity. So we're in a situation where really we're approaching infinity. We can get more and more rectangles. We'll never have an infinite number of them, but the idea is just keep throwing in more rectangles. So theoretically, what we do there is we just take the limit as n approaches infinity, okay? So what I'm going to do is I can use any one of these formulas. Now, it's computationally easier from a theoretical standpoint to use the right-hand version, but really any one of these guys could work. So if I take this guy and put him here, and then I just take the limit as n approaches infinity, that's basically saying, well, we're cutting it up into an infinite number of subintervals to create space for an infinite number of rectangles. So we take the limit, and that's how you'd find the area under the exact area under the curve. This idea, by the way, these things, when we're adding up all these areas through any of these methods, it is said that we're taking what's called a Riemann sum. Now, there are two versions, as you can see. There's the finite Riemann sum that only uses n rectangles, where n is just some number, 5, 6, 10, 10,000. It's just some number. Or there's an infinite Riemann sum, where you're using an infinite number of rectangles. And to get that to theoretically make sense, which I'm doing a lot of hand waving here, it's really just taking a limit as n approaches infinity. Okay? And again, don't worry too much about the formulas right now, but we have a shorthand for that. To write down this Riemann sum, the infinite Riemann sum, we use this formula here, okay? Now, this is like an elongated S. The interval, the endpoints of the interval that you care about, the A and the B, go on that symbol. You put the function under which you're finding the area, right? So this is we gave our function the name, this is f of x. So we have this symbol, right? And that symbol, whenever we write that, it's just a shorthand of writing this. It's just another way of writing that. Now, this is because this is a very elongated S. The S stands for sum because we're summing up a bunch of things. And so that's kind of the idea behind the notation. Once we have that notation, the infinite Riemann sum, we give it this name. It is called the definite integral of f of x on AB. And now you can see why the title of this section is called the definite integral. We have found a way to find the area under a curve by using a bunch of rectangles. Once we figure out a nice formulaic way to do that, we say we've developed a Riemann sum. Once you take the infinite Riemann sum, which it gives you the idea that you're using an infinite number of rectangles, we call that the definite integral of the function on the interval AB. And this is the symbol that we use, the symbols that we use to describe that idea. Okay, now in terms of these, this symbol, this is what it looks like. This is called the definite integral. I just want to know how to actually talk about this. So this here, this is called the integral sign. So it's called an integral sign. The B, this is called the upper limit. The A, this is called the lower limit. The function f of x in this case is called the integrand. And the dx, this is called the differential. And the whole thing is called a definite integral. So this thing is called the definite integral of f of x, the function on the interval. the dx kind of tells you which axis you're slicing up the subintervals in. So because we're slicing along the x-axis, where we have the delta x, that's where this notation comes from. So we have this function where we're finding the area under that curve by slicing up intervals on the x-axis between x equals a and x equals b. And this symbol means we are finding, it is finding the area under f. And I put that in quotes for a reason. We'll talk about that later. On AB. So that's what that symbol actually means, right? So in order to compute this number, we'd have to be able to compute that, which in this class, we're not actually going to do it that way. In a 1206 class, we would have done that, but not in this class. I'm going to give you guys the short way of actually computing this. But this is the symbol. This is what you would write down. This means find the area under the function from a to b. We called it a definite integral of f of x on ab. Now, before I show you how to actually compute those, let's actually go back and make sure that we understand the finite case, because this is something I'm definitely going to actually test you guys on. So here's how a specific example might look. Okay. So like I said, you won't need to write down any of the above formulas. I just really wanted to talk about the idea behind what we're doing and give you some sort of context here as to what we're doing. But as for what you need to be able to do on paper, and I'm going to show you how you can actually figure this out without even having to memorize any of these formulas right here. So I might give you a function and the interval, and I'm going to tell you approximate the area under this function using 4 subintervals. Or I can say instead I can say something like here, or using 4 rectangles. Or I could say something like using n equals 4, right? There's going to be a way where I'm going to tell you how many subintervals or rectangles I want you to use, and it's going to be there. So there's the function. So here's x squared plus 1. I am on the interval 1 to 5. I want to approximate the area under this function using 4 guys and left-hand endpoints, right-hand endpoints, and midpoints. Now, in general, I'm not going to ask you to do all 3 for any particular function, but I'll actually like one of these. But I want us to do all of these so that you can see an example of how each one would actually look, right? So this is the important thing. This is the example that you're actually going to need to be able to actually do and be able to reproduce, right? So this is just to satisfy your curiosity, and hopefully some of you enjoyed the exposition of what we were doing, why it kind of works out that way. Theoretically, you won't need to know how to explain all of that, though. Theoretically, well, not even theoretically, practically speaking, what you need to do is to be able to do the finite case here. So let's actually get to that. Let's worry about the left-hand endpoints for the time being. How would we actually do this? Okay, so let's actually begin. Let me take a sip of my coffee here. All right, so let's actually get to it. Let's actually do some examples. Been just talking for such a long time. Let's actually get to something interesting. Okay, left-hand endpoints. So here's the idea. What I like to do is, 1, I like to draw the interval and subintervals. Well, we could do this first for a second, but let me do, maybe this will actually be nicer. First thing you want to do for these is find delta x. Then I'm going to draw it, okay? So remember what I told you delta x is, and this is actually one of the forms that you do need to know. So the one here that I highlighted, you are going to need to know that delta x is b minus a over n. So in this case, the interval here is 1, 5. Of course, this is a, this is b, and we know that n equals 4. So your delta x is going to be b minus a over n. In other words, it's going to be 5 minus 1 over 4. This is going to be 4 over 4, which is going to be 1. So your delta x is 1 in this case. And I think this is something that I actually want you guys to write out, so that should be in black. Okay? So the first thing you're going to do to solve one of these problems is you're going to find your delta x. The second thing you're going to do is to draw them. Now this will help you not having to memorize this annoying formula. You are going to be able to actually just look at a picture and know what numbers you're going to want to do. So just drawing a representation of the interval. Here's 1 to 5. I know I want to cut this up into 4 equal pieces. And I know that my delta x is 1, which means to get to the next piece, the length of this one thing is length 1. So to go from here to there, well, that would bring me to 2. Then I would jump units of 1 until I get to the end. In other words, every time I'm going from one to the other, I'm adding delta x. And then to get to the next one, I add delta x. Then to get to the next one, I add delta x. And to get to the next one, I add delta x, right? Because the length of each of these is delta x. Okay. So now what I'm going to do is pick the necessary numbers. How do I know what the necessary numbers are? Well, the part A, I'm using the left-hand endpoints, which means the necessary numbers are, looking at each subinterval, I want the guy on the left. So if I look at the first subinterval, 1 is on the left. If I look at the second subinterval from 2 to 3, 2 is on the left. If I look at the next one from 3 to 4, 3 is on the left. If I look at the next one from 4 to 5, 4 is on the left. So it means that these are the 4 numbers that I'm going to pick. These are the numbers on the left. And that brings us to the next part. So 3 set up the Riemann sum. Now, what this is actually going to look like now is, well, we're doing L sub 4. So this is the left-hand Riemann sum with 4 subintervals. Okay. Now that is going to be equal to, well, these are all the numbers I'm picking. So it's going to be delta x times, well, f evaluated at 1 plus f evaluated at 2 plus f evaluated at 3 plus f evaluated at 4. Those are all the numbers that I picked. And now I'm just going to plug it in. So what was my delta x? Was 1. So this is just a 1 here. And what was my f? Well, remember our f of x was x squared plus 1. So f of 1, well, that's 1 squared plus 1. F of 2 is 2 squared plus 1. F of 3, 3 squared plus 1. F of 4, 4 squared plus 1, right? So those are all, these are each of, so this guy here, that's my f of 1. This guy here, well, that's my f of 2. This guy here, that's my f of 3. This guy here, that's my f of 4. And at this point, you just, you just calculate that. So this is going to be, well, 2 plus 5 plus this here is going to be 10 plus that's going to be 17. 16 plus 1. So that's 7 plus this, that's a 24. So this is 34. So now our area is going to be approximately equal to this approximation with 4 subintervals, and this gives us 34 as the answer. Now, hopefully that was clear. And so that's basically what a problem would actually look like for you to actually write it out. Okay. Now let's do another one. So we're going to do the same thing, but now we're going to do the right hand. Down here. B, right hand endpoints. So let's go through this again. So step 1, find delta x. So you're going to write delta x equals b minus a over n. This is going to be 5 minus 1 over 4. This is going to be 1. Step 2, sketch interval. And pick numbers. So the interval that we care about here is 1 to 5. Again, that's the problem. We want the area under f of x equals x squared plus 1 on 1 to 5 using n equals 4. Which means this interval, I'm going to cut it up into 4 equal pieces. I start at the first endpoint and add delta x, keep adding delta x. So this will give me 2, 3, 4, because I keep just adding the delta x here. Then I want to pick the right numbers. Pardon the pun, but we want the numbers on the right numbers. 2, 3, 4, and 5 would be the right numbers here, because on the first subinterval between 1 and 2, 2 is on the right. On the second subinterval between 2 and 3, 3 is on the right. On the third subinterval between 3 and 4, 4 is on the right. On the fourth subinterval between 4 and 5, 5 is on the right. So the numbers I picked here are the numbers 2 through 5. And this brings us to the last one, set up the Riemann sum. And so this is basically where we're going to realize that the area that we care about is going to be approximately equal to the right-hand rule with 4. That's delta x times f of 2 plus f of 3 plus f of 4 plus f of 5. And now you're just going to plug in the numbers and actually calculate that. So our delta x was 1, f of 2, 2 squared plus 1, f of 3, 3 squared plus 1, f of 4, 4 squared plus 1, f of 5, 5 squared plus 1. So that's 5 plus 10 plus 17 plus 26. Right? Now, hopefully you're following with that. So it's 5 plus 10 plus 17 plus 26. So this one is going to give us 58. Now, I want you to notice that it's actually higher than the last number that we get, but of course, these are all approximations. None of these are going to be the exact areas because we're using a finite number of rectangles. So using the left hand, we got a 34. And you guys can we can talk about next time why you think this is actually smaller than this. But using the right hand, it's actually 58. So as you can see, this is a problem in its entirety right here. So the problem is not that long, but knowing what these pieces are, that's what it took a long time to explain. So let's actually look at midpoints. How would this work? Well, we'll go through the same idea. Now, hopefully you do remember the function. Okay, so we know our f of x equals x squared plus 1. We are on the interval 1 to 5, and we're using n equals 4. We want to use now midpoints. The idea is going to be the same. So step 1, find delta x. Delta x is equal to b minus a over n. This is 5 minus 1 over 4, which is 1. Step 2, jumping to step 3. Sketch interval, pick numbers. Now this is 1 to 5. Now I know this is going to be that, that's going to be that. And so this is going to be 2, 3, 4, because we're adding delta x. Now remember, with the midpoint, we actually want the guys in the middle. So we actually care about these guys over here. So for the first one, what we can do is we can actually just average these two numbers. So if I take 1 plus 2 all over 2, that's 3 over 2, or 1.5, that's going to be the first number, 1.5. And then I can, to that 1.5, add delta x. So that'll be 2.5. Add delta x. That'll be 3.5. Add delta x. That'll be 4.5. So these now are the numbers that I want. Which brings us to the next step. 3, set up the Riemann sums. So the area is approximately equal to the midpoint approximation with 4 rectangles. This is going to be delta x times, well, f of 1.5 plus f of 2.5 plus f of 3.5. Now, personally, I would prefer fractions, but I don't know. Kids don't like fractions these days. Okay, so that's going to be 1. This will be 1.5 squared plus 1. This will be 2.5 squared plus 1. This will be 3.5 squared plus 1. This will be 4.5 squared plus 1. And so let's actually see what that would give us here. So it's 1 plus 1 plus 1, that's obviously 4. And we want to add to that 1 plus 5 squared, and 1.5 squared, 2.5 squared, 3.5 squared, and 4.5 squared. So that is around 45. So it's in between the left and the right hand for this particular example. Now, you can, no, so that's the whole problem at a glance. That's us calculating it. Now, of course, in what I wrote in the green, you don't really have to write down, but you should know the process. That's why I wrote the steps out. Now, one thing you can realize why this might be the case. Why did these numbers work out the way they did? What does x squared plus 1 looks like? Well, it's a parabola, right? But the right side, of course, is going to look like that, right? Of course, the left side we don't care about. We care about the area between 1 and 5. So we care about this area here. Now, of course, the left hand you would expect it to give you something smaller than the actual area, right? So you would expect that the left hand should probably give you one of the smallest answers here, while the right hand should give you something that's a little bit bigger than the actual area. Whereas the midpoint would give you like something in between. So your midpoint your right hand, and your left hand, right? So you expect for this particular example, for this particular shape, because it's moving up as you go from left to right, the right side, the right hand approximation will always be bigger. The left hand approximation is going to be smaller. The midpoint should be in between them, right? Because you'll see the green rectangles are smaller than the black rectangles are smaller than the red rectangles. So it actually makes a lot of sense that this answer is smaller than that answer, and this answer is in between the two. When you actually start thinking geometrically, it'll actually make sense. Now, none of those are probably the actual answer. And so to find the actual answer, that comes down to us actually computing the definite integral, right? It will be the case that we will need to somehow find the limit as n approaches infinity of this. Now, in this particular class, we're not going to do that. We're actually going to find a shorter way of computing this, which is what the next lecture is about. So that's it for today's lecture. To recap, I don't even know. At this point, I don't even know how much. I paid attention to what time I started last time, but when I ran into glitches and I restarted, I didn't even pay attention to the clock. I don't even know how long I've been talking. So today's lecture was about solving the area problem. The idea, we want to find the area of an irregular shape, slice it up into a bunch of smaller shapes that we know how to find the area, and add them all up. That, though, is not very efficient, very time consuming. So what we want to do is we threw it on the XY plane. First, we dissect it less, let's say into strips, vertical strips, just to make computations easier. Throwing it on the XY plane, what we realize is that to make it a function, we can just really find half the answer at a time. Essentially, after that, we just make the shapes look a little bit nicer, rectangles. And so now the idea is to find the area of this random shape. It's equivalent to me finding the area under a curve, because once I know how to do that, I would know how to solve this problem. And essentially, how I'm going to do that is to use a bunch of areas of rectangles to approximate that. Now, there are several different, now the idea is the more rectangles I use, the better the approximation. And an infinite number of rectangles would give me theoretically the exact answer. And so now when we start to get to the formulaic view, there are several ways that we can set up how to construct these rectangles. The ones you need to know are the left-hand, right-hand, and midpoint rules. And these are the formulas that are actually govern them, but you don't need to know those formulas. What you do need to know about, though, is the definite integral, what it means. In the next lecture, I'll actually show you guys how to compute that. And here's how to actually do the left-hand rule, the right-hand rule, and the midpoint rule in calculations for the finite case. So a problem that I would ask you to do in this section would look pretty much exactly like this. So I'm going to give you a function, I'm going to give you the interval, I'm going to tell you I wanted to approximate the area under this function using some number of intervals. Now, usually I'm going to ask you 3 or 4, probably expect 4. And then you go through this 3-step process. And depending on what I ask you, whether the left hand or right hand or midpoint, you'll know how to pick the right numbers to plug into the function in order to compute the approximate area. So we are going to stop there. So I don't actually know how much time we spent. I didn't pay attention again. Hopefully we didn't go too much over time. But that's basically all we need to know for this section. Not to take any more of your time, we're going to end right here. Have any questions, drop them down in the comment section or email me. And I'll be having classes with you guys live next week. So hopefully you can ask me questions in real time and hopefully it'll be a little bit more clear. But what I did towards the end there, that is what I need you to know for this section. That being said, have a good night, stay safe, and I will see you guys in the next one.